Okay, for those of you just joining us on the recording, this is the beginning of the actual math part of the lecture. So let me share correct screen. Looking at the chat, by the way, is it actually someone's birthday? Is it yours, Megan? Well, happy birthday. So, okay. I'm going to turn off the video so that nobody can see how unsafe I'm being by not wearing a mask during this lecture. Okay. Oh, actually, hold on. Just give me a second. I just have to fix something. Now we're ready to go. Okay. Oh, it looks like that's actually still sharing. Okay, good. Okay. So, all right. So we were covering optimization problems the other day, and we had gotten through. We'd gotten through the farmer problem, and I believe I had done the rectangle problem, or did I do the open top box? Can someone remind me? Because I think I did them differently in two classes. Rectangle. Okay. Hold on just a second. I just want to check for sure. Rectangle. Okay. So let's do the open top box. Okay. So what we're going to do is we're going to find the open top box with the largest volume. This is one of the problems. This is where we start to get into types of problems that require a little bit more ability to visualize different scenarios, because you have to be able to translate them into the word problems. The other thing also that's worth noting is that when you did probably the farmer problem in pre-calc, the assumption you were making, I'm just going to write here for a second, then I'll erase it. The assumption you were making when you did the farmer problem was that the objective function you got was going to be something like that. So it was going to be quadratic. The advantage to it being quadratic is that you know that it's going to have this shape, and you know that its maximum is going to be there, and we know that the location of the maximum is x equals negative b over 2a. Or you could have just plugged it into a graphing calculator and found it. So you didn't really need calculus to solve the farmer problem when you did it in pre-calc. I just used it to show you the pre-calc way to do it. Let me show you the calculus way to do it. The issue, though, with when you get beyond problems that come out to a quadratic objective function, is that you can't just use a simple formula like the vertex is at negative b over 2a. You have to use calculus to be able to actually find the location of the vertex. So, okay. So the previous problem we did, the one with the rectangle inscribed in a parabola, that comes out actually, that comes out to a cubic function, and this one likely will too. So here what we want to do is we want to find the volume of the largest open top box that can be made from a piece of cardboard 24 inches square by cutting equal squares from the corners and turning up the sides. So what we have here is we have a 24-inch on a side. In other words, each side is 24 inches. And what we want to do is cut out equal size squares on all corners and flip them up. So each square that we cut out is going to be x by x. And what that does is it's going to leave this amount. Let me just draw it in a different color here. This purple area that you see here, this is going to become the bottom of the box. And it's going to have sides that are 24 minus 2x. In other words, I'm taking out a byte of x on each side of the box, leaving, so I'm going to take out x twice from the 24, leaving only 24 by 2x. And then that's the same here. So I've got 24 by 2x on that side. And then what happens is the purple area becomes the bottom of the box. So I flip everything up. And what I get is a box looks like that. That's actually one of the best boxes I've ever drawn. I'm really terrible at drawing these things, but this is going to be 24 minus 2x on that side, 24 minus 2x on that side, and x on that side. To question. So each smaller square is 24 inches, or is the length 24? If you mean by the smaller squares, do you mean like that square? Yeah, no, that's going to be x by x. I'm cutting off x on that side. Okay. So the idea is, of course, when I flip this up, it's actually going to be this length here that becomes the height of the box. So that's why that gets an X when I actually draw the full box. So the box is going to be, there's no way to really do the top with this arrangement. So we're just going to call it an open top box. It's, going to be open here. So, all right. So now what we do is we want to find the quantity to be optimized. So quantity to optimize. And that's, of course, going to be the volume. So the next step is we have to write volume as a function, some variable. So we know that the volume of a box is the volume of a rectangular box is going to be, let's call that length, let's call that width and height. So it's going to be length times width times height. But recall what I said the other day about what sort of function we need. Does anyone want to recall what the main thing about the objective function is? Eric, excellent. It needs to have one variable. So we're going to need to get everything down to one variable. Fortunately, we have that because we have the length and width and height all written in terms of x. So I'm going to write the volume of the box, color consistent. The volume of the box as a function of x is going to be 24 minus 2x, 24 minus 2x times x, where this is the height, this is the width, This is the length. So that's going to come out to, I multiply everything out, that comes out to 576 minus 48x plus 4x squared times x, which if I rearrange everything a bit, which I'm going to do, comes out to 4x cubed minus 48x squared plus 576x. Okay, so that's the objective function. And we also need to find the domain. Remember, we're hoping that the domain comes out to a closed and bounded interval because those are the easiest functions to optimize. All you have to do is check the critical numbers and the endpoints. We'll see a little bit later today. We're going to see the we will see so we'll see a couple of examples where there are no endpoints to the intervals, but in this one we'll do one more with endpoints. So what is the domain of this function? Not the mathematical domain, but the practical domain in terms of in terms of what we could actually build. Correct. So it's got to be greater than 0. So we know that x has to be, in fact, I'm going to call it greater than or equal to 0 because we could always just build a box of 0 height. It would just have no volume and it's not going to be the answer, but it's not infeasible to build it at least. You just cut out no squares at all. So what's the maximum size square that I can cut out? What's the maximum value of x? Everyone has said, most people are saying 24, but it's actually is one response of 12. Remember, we're going to cut out 2 squares of size x. So if we cut out 24, there's nothing left to cut out for the other square. Since these are going to be the same value x, the most we can cut out is 12 on each side. And of course, that's going to leave a box that has a 0 area base, which is also going to be 0 volume, but that's the most we could cut out. So x is going to be less than or equal to 12. So the domain is 0, 12. And once again, we have we have a closed and bounded interval. So, all right, let's turn the page. On the page, as Bob Seger might say. And so recall, so what we want to do now is optimize. Recall that v of x we found was 4x cubed minus 48x squared plus 576x. So that gives us v prime of x equals 12x squared minus 96x plus 576. We're going to factor that a little bit. It'd be a little bit easier to work with if we factor out the 12. So let's call that 12. That gives us x squared. 96 divided by 12 is 8. 576 divided by 12. I know you don't know that one in your head, but I did this in advance. 48. So that equals, see, yeah, okay. That comes out to 12. And this is sorry, I think I made a mistake on this. Let me just check one thing. Oh, no, that's right. Okay. That's right. Okay. By 16. Yeah, that's okay. That comes out to x minus 4. Sorry, I apologize for this. My notes are just have an error in them, and I just need to fix it. Give me just a second. Strange. I've done this problem like many times, and just bear with me for like a minute while I just find the mistake. Sorry, just hold on. This is going to just. Okay, I got it. This, I believe, should actually be 96. So 24. There we go. That should give the correct answer. Okay. So okay, we're now ready to resume. Apologize to that. Yeah, let me go back to the last page so you can see. So okay, so you can just see what I fixed. I had written in this spot, I had written a 48 because I had only multiplied 2 by 24 once, and I had to multiply it by it twice because we were squaring the 2 by 24 minus 2x. So that's 96. Got it? Okay, I'm going to go ahead now. Okay, so we're at this point now. We found this was the correct objective function, 4x cubed minus 96x squared plus 576. We find the derivative of that. And ultimately, the idea is that we want to factor it because we're going to try to set it to 0. So that comes out to x minus 12 minus 4 x squared. Correct. Thank you. Okay. So, all right, what we want to do, having found that this is in fact the correct derivative in factored form, what we want to do is find v of x equals 0. So that gives us, that means that either x minus 12 equals 0 or x minus 4 equals 0. So x equals 12 or 4. We were already going to test 12 anyway because it's one of the endpoints of the interval. Recall that the domain was 0, 12. So okay, so we have so what we want to do is test x equals 0, x equals 4, and x equals 12. So again, remember the biggest mistake people make is they plug they plug these values into the derivative. What you're trying to do is find the greatest and smallest values of the original function, the volume. And which of these values gives us the largest volume? So you have to plug it into the original function. So v of x, we know what v of x is because it's up here. So we want to find v of 0. And clearly, since we have x in all the terms, that's just going to give us 0. V of 4 is going to be 4 times 64 minus 96 times 4 squared is 16 plus 576 times x is 4. You add that up, that comes out to 1024. And v of 12, we already made the geometric argument that if I take a byte size, if I take a byte of size 12 on each side of a 24-inch side, I'm just going to get 0. So that would give us a 0. That would make this area 0 like that. If you actually do the math and plug in all these numbers, you're going to get 0, but that's the geometric argument. So that's 0. You can always just find that just by plugging in those numbers. So what we can easily see is that the greatest possible box you can make is going to have a volume of 1024. So the dimensions of the box are going to be x equals 4 and 24 minus 2x equals 16. So recalling, box is going to look like this. So far, the endpoints have always resulted in 0. In geometry problems, it often does. Just because usually you're choosing, you're choosing the endpoints to have the most extreme cases. The most extreme case of a rectangle is either that it has no width or no height. Most extreme case of a rectangular box is that it has no height or it has no of some other dimension. It's not, I can't say it's universally the case, but it's in many of these problems it is. It's actually hard for me to find a problem where it doesn't come out to that. So, okay, so what we have here is this is going to be 16, 16, and 4. So the box be 16 by 16 by 4, where 4 is 8. There we go. Can you explain how you got, sorry, I was reading a question. Can you explain how you got 12 as part of the domain again? Yeah, it's just, it just comes from the geometry that the most, if I'm going to cut out x on both sides of a side, the most I can do is cut out 12, because if I cut out 12 on each side, that comes out to 24 inches that I've cut away, and there are only 24 inches. V of 12 equals 0. This question is, can I explain how V of 12 equals 0? Well, for one thing, what you could have done is just, if you plugged in 12 into the original V of X, that appears, I'm trying to see if the pointer works, that appears at the top of the page, you would get that. I just didn't want to spend the time doing the arithmetic. But geometrically, if you actually took 12 inches from each side of the box and from each side of one side of the original piece of cardboard, you would be left with 24 minus 2x is equal to 0. So you'd have a 0 by 0 square as the base, and there would be, you'd have a box that was very, very tall but had no width on the bottom. Okay. It doesn't problem, actually. Okay. So actually, I want to do this one. This is a good problem, but it's another one with an open domain. So I'm sorry, with a closed domain. I want to do one that has an open domain. So let's do this one. Okay, let's minimize the amount of metal needed to build a cylindrical can of volume 900 cubic centimeters, so that we want to make it so it uses the least amount of metal. Let's just draw here what a can looks like. I mean, I know, as most of you know. Let's see. So if you think about what a can is, it's got a radius and it has a height. So let's see. The surface area of a cylinder that's what we're really trying to optimize. Is what we want to do is optimize surface area of a cylinder plus ends. Strictly speaking, a cylinder is actually just the sides of what you think of as a can, and the cylinder doesn't actually the geometric figure cylinder doesn't actually include its top and bottom. That's why I have to say that I want to find, in order to make an actual can, I need to include the ends of the cylinder, because they're not actually included in the definition of the cylinder. So when we say we want to use the least metal, what we're really saying is we want the surface area to be a minimum for this can. So what we need to do is write the surface area as a function Okay, so the surface area of this can is, first of all, the sides. The circumference of this circle is going to equal 2 pi r. And if I kind of unroll it, what I would get is sort of this unrolled rectangle like this, where the bottom of the can unrolls to be one side of the rectangle, and it's going to be 2 pi r, and the side of the rectangle is going to be h, like that. So that's what the side of it is. So the surface area of a cylinder is going to be 2 pi r h, where that's the side of the cylinder. And the top and bottom are just two circles, so pi r squared and also pi r squared. The h doesn't come into it because that has nothing to do. The height of the cylinder has nothing to do with how big the top and bottom are. They're just circles. So this is the top. This is the bottom. Okay. So the problem with this, of course, is that it's not all one variable. So we need to somehow get rid of this h. Now, the way we do that is this. Note that the volume of the cylinder, not sure if you remember this from geometry, but what I do is I take the area of the base and multiply it by the height. So the volume of a cylinder is pi r squared h. And we also know from the problem statement that that's going to be a fixed 900. So that gives us h is equal to 900 over pi r squared. So that means that S is going to equal 2 pi r times 900 over pi r squared plus 2 pi r squared, because I'm going to multiply I'm going to add the top and bottom together. So that equals, simplifying that first expression, that's going to give us 1800. 2 pi's are going to cancel. And one factor of r is going to cancel, giving me 1800 over r plus 2 pi r squared. So I now have the surface area as a function of the radius, which is the 1800 over r plus 2 pi r squared. Now I have an objective function in terms of one variable. Okay. Everyone with me so far? So now we need to consider the domain. Okay, so let's go back to this picture. What is the smallest radius? So I'm trying to write S in terms of radius. So what's the smallest radius that I can have? 0. Okay. So we know that R, in fact, I can't even have 0 because if you look at the function, I would be dividing by 0. So here, this is the first time we're going to see an optimization problem where the domain is not a closed interval. Because r actually has to be greater than 0. I can't put 0 in the denominator in that expression. Okay, now that's the smallest r. What's the largest r? Yeah. So what I could do is I could just to make a 900 cubic centimeter can, I could just make a very, very wide and very, very small and very, very short can. So r has no maximum. So all we can say is that r is less than infinity. It's just any positive finite number. So the domain is 0, infinity. Okay, so this is already going to give us a different type of problem because we're not going to be able to use the simple procedure for optimizing on a closed interval. We're going to have to reason differently to figure out what the we have to reason differently to figure out what the min and max are. Okay, so looks like there's some confusion about why the end of the domain is infinity. The answer is that I can squash this can as much as I want, but in order to keep, this is going to be, let's say I have here height of 0.001. So let's say, let's just say that, the height of the cylinder is 0.001. I can still make a 900 cubic centimeter. I can still make a 900 cubic centimeter cylinder. I just have to make the radius very, very big to do that because what I know is that pi r squared times the height of 0.001 still has to equal 900. So that would give me pi r squared is going to equal, divide by 1,000, and I get 900,000. Or r is going to equal the square root of 900,000 over pi. So you see, and that's just that's one extreme example. But if that's not big enough for you, I could set the height to be 0.00000001, and I'd require an even bigger radius. So there's just no limit as to how big I might have to make the radius to satisfy this condition that the volume is 900. It just depends on how short I want to make the can. Just waiting for a question. No. Let me just go back to the previous problem for a minute. There's a limit as to how much I could cut out of how much X I can cut out, because I only have 24 inches on a side. So there's no way that I could cut out, like, let's say infinity. I have no way I could cut out, say, 100,000 inches on a side. So yeah, I mean, these problems, they often seem a little bit more like physics than they do like math, because it's not that mathematically I couldn't put some sort of bounds on this. It's just that we're talking about are the physical limitations of the problems. The problem where they don't give you any numbers, like problem 12 from the homework. I don't know what problem 12 is. I'll look at that later. Right now I'm doing this problem. So, okay. What's the difference between this and the other optimization problems? The difference is, I mean, for one thing, the geometry is different, but the main point of this problem is to demonstrate what happens when you can't define a closed and bounded interval, because intervals that are closed and bounded, where you check the endpoints, have this very simple optimization procedure, and we're going to have to make a slightly different type of argument. Okay. I was waiting for some questions, so I just wanted to try to clear up any confusions before we go on. So the question is, are 0 and infinity still endpoints because it isn't a closed interval anymore? So 0 is certainly an endpoint, because it's possible to be an endpoint of an open interval where the interval just doesn't include its endpoint. Infinity is not technically an endpoint because it's not a number, but so it's just the way we describe the interval from 0 to infinity. Anyway, so we want to do is optimize S of R on the interval 0 to infinity. The thing to observe here is that if I find the limit as x approaches infinity of 1800 over r plus 2 pi r squared, what you'll see is that this term is going to go to 0, and this term is going to go to positive infinity. We covered that in chapter 2. So this limit is equal to positive infinity. It's also the case that if I look at it on the other side, x approaches 0, I've got to be a little careful, because on the number line, I'm going from 0 out to infinity. So I'm actually considering only from the right what happens as I approach 0. I'm not interested in the left, because it's not part of in what happens from the left of 0 because that's not part of the domain. Cross that out. So as I approach x from the positive side, 1800 over r plus 2 pi r squared, then by substitution, that's going to be 0. But here I've got a positive number over a very, very tiny positive number, and I'm approaching infinity. So this is also going to be infinity. So what that tells us is that whatever this looks like, it's going to look like this. In other words, I'm approaching positive infinity as I get close to 0, and I'm also approaching positive infinity as I get close to, as I actually approach infinity on the x-axis, or the r-axis, I should say. This is s as a function of r. So what that means is that whatever the minimums are, it's going to be one of these points. It's got to be one of the critical numbers that appears in the interval. So all we have to do is find those critical numbers. So so here, once again, we have s of r. Well, actually, I wrote it up there. There's s of r. So let's just find s prime of r. So that's going to equal negative 1800 over r squared. That's the derivative of 1800 over r, plus derivative of 2 pi r squared with respect to r is 4 pi r. So what we just have to do is we can see that since the interval doesn't include 0, there are going to be no places where this is undefined. I don't have to consider r equals 0 because it's not in the domain. And all I have to do is set s prime of r equal to 0. It implies that 4 pi r squared minus 1800 over r squared equals 0. That gives us 4 pi r squared equals 1800 over r squared. And, sorry, that's r. 4 pi r, not a squared either. I just looked at the chat, and yes, somebody pointed that out to me. So, okay, so we have 4 pi r equals 1800 over pi r, 1800 over r squared. We're going to multiply both sides by r squared, giving 4 pi r cubed equals 1800. Divide both sides by 4 pi. That's going to give us r cubed equals 450 over pi. So r is going to equal cube root of 450 over pi, which is approximately equal to 5.23. So that's the radius. We know from an earlier part of the problem that the height is 900 over pi r squared. So that's going to be 900 over pi times 5.23 squared, which is approximately equal to 10.46. So n should be radius 5.23 centimeters and height 10.46 centimeters. Okay. So that's the answer. Now, the difference in this problem is that in order to be able to say that this was actually a minimum, I had to be able to make some sort of geometric argument about what was going on the other sides of the function. We saw is that as the function approaches 0 or infinity, it grows on in the vertical sense up to up to infinity. So that means that if this is going to be plus infinity and this is going to be plus infinity, something in between it is going to have to be lower, and we know that minimums can only occur at critical numbers. So if there was only one critical number, that's all we had to say, was that that was the minimum value. Um, had there been multiple critical numbers, we would have actually had to compare them and see which one was the lowest. Um, but in this case, since there was only one, and it's between infinity on either end of the domain, we can say that that's going to have to be lower than either end of the domain, and therefore it must be the minimum. Are there any questions about that? Okay, good. Okay, so I just want to do a little bit more. I want to do a few more of these. Um, Somebody just asked, it was Miguel who just asked about problem 12. I actually can do one like that in a minute. And I'll just show you. I think you said there are no numbers, but there actually are numbers in there, and I'll show you how to set up. Okay. So what I want to do actually is, since the setup is the hard part and the solution isn't all that different, I just want to show you a slightly different type of problem. Um, so this looks kind of like the fence problems that we've seen, but it's a little bit tricky because I'll tell you what a lot of people get wrong. So a fence must be built around a rectangular area of 1,600 square feet. Uh, the fence along three sides is to be made of material that costs $120 per foot, but the fourth side is going to be made of a material that costs $40 per foot. I guess we can think of that as maybe that's the part that's going to go by the river. The pigs just need a small deterrent to avoid jumping into the river. They need the full expensive fence to prevent that. So what I want to do is find the dimensions of the rectangle that would be the least expensive to build. Most people look at this and say, oh, it's a fence and a rectangle building problem. Surely the quantity to be optimized is area. And even if you look at even if you look at the text of the problem carefully, some people will say, no, that's not right. And then they'll still end up writing an objective function for area. So I just want to be sort of careful about how we set up the objective function. I'm not going to solve this problem all the way through. We're just going to find the objective function and the domain. So what is the quantity to be optimized here? Ooh, a little bit of a dispute here. So yes, the quantity to be optimized is the price cost of the whole fence. We're trying to find the rectangle that would be the least expensive to build. Now, someone said perimeter. That would be true if the perimeter completely defined the cost of building the rectangle, but it doesn't, because the cost of three sides is different from the cost of the fourth side. So we have to know not only how much perimeter there is, but also um, not only how much perimeter there is, but also where that perimeter goes. And we also have to meet the constraint that the area of the rectangle still has to be 1,600 square feet. So take a minute and actually no, let me show you how to do this. The If I draw this diagram like this, what I'm going to do is I'm going to have know I'm doing this backwards. I know we usually put X on the horizontal and Y on the vertical. I'm just going to draw it this way because it's the way I did it in my notes. So I've got a rectangle that's X by Y. And there are a couple of things about it. First of all, 3 sides are going to cost $120 to build. So the cost of building this side is going to be 120x, and the cost of building this side is going to be 120x. The cost of building this side is going to be 120y, and the cost of building the fourth side is going to be 40y. Okay, so I'm going to give you about 2 minutes, and I just want to see if you can come up with, I mean, if you don't look in the notes, if you've already seen them, but just try to come up with the objective function here, and then I'll write it out, and then we'll go on to figure out what the domain is. Don't say anything yet. Let's just share our answers in about 2 minutes. Okay, there's an answer up that's not quite right, but anybody feels they've gotten the answer, why don't you post it? Let's see. Sorry, there are so many different forms of the answer now. I just have to convert them. Let's see. One of these is sort of on the right track. I haven't seen it yet. I think Jeffrey's answer is correct, although that's not the form I have it in. So let's just go over how you would do this. So in order to find the cost function, what you need to do is add up all the sides. So the cost is going to be 120x plus 120y plus 120x plus 40y equals 240x plus 160y. The thing you have to realize, though, is that since the area is equal to x times y, and we also know that the area has to be fixed at 1600, that means that y equals 1600 over x. So I can rewrite this. I'm going to rewrite this slightly. This is going to be 80 times 3x plus 2y. And then I can write that as 80 3x plus 2 times 1600 over x. So this is going to be sorry, c of x equals 80 times 3x plus 3200 over x. I think if I multiply, I think if I multiply 80 by 32, I think I actually do get 256,000. So that is okay. So that is the correct answer, in which can come in various forms. The point is that if you notice, what this is giving is cost as a function of length of one side. So that's your objective function. Okay, now what's the domain? So yeah, so one side is, we know that we can't make x equal to 0 because we get division by 0, but we can make it basically any size that's bigger than 0. So I have x is greater than 0. And I think I saw, infinity on the other side, because there's, of course, no limit as to how, for the same reason as in the other problem, there's no limit as to how big I can make x, as long as I'm willing to make y very, very skinny. So, so that's the only limitation. The domain is 0 to infinity. So basically, you could just optimize this problem like you did with the other, like we did with the other problem. It's just that the thing that I predicted is that what tripped up a couple of people at the beginning was, they wanted to write the objective function as some other quantity other than cost, and you have to really think about how that would be done. So, you really have to think about what the, what you're trying to optimize and how to write that actual physical quantity as an objective function. So, okay, let me do a few more of those. Any other questions? Okay. So a couple more types of problems of this. There was a request for number 12, and since I have a little time, I can do that. We're actually doing nicely on time for the class in general. So let's see. Tube length 4 meters to be bent into L shape. Where should the bend be to minimize distance between the ends? Okay. So let me just do this. There are a couple of questions. Let me just do this one, then I'll go back to answer the question about why this is different from the farmer problem. So, okay. So, okay. So this problem, this is actually a good example of a problem. So what we've got here is 4 meter length of tube. We want to bend it someplace. So what it's going to become is this. And what we're trying to do is minimize this distance. So if you think about it, what we can do is we can put the bend here. Let's draw that as the place where the bend goes. So the idea is we're going to bend the pipe. Let's say x meters. X meters from the from one end of it, and what that means is that this length here becomes 4 minus x. If I draw this, that means that that's going to be x meters long, and this is going to be 4 minus x meters long. I realize once again I'm putting the x on the vertical axis, but it doesn't really matter what I call it. So you can kind of imagine that if this is now going to be a right triangle. So the question is, I'm trying to minimize that hypotenuse. So what I know is that distance is going to equal the square root of x squared plus 4 minus x squared. So that's going to be distance as a function of where I put x. And as you can see, the most I can do, the extreme, one extreme of where I can put x is going to be, I can put x 0 meters from the end. The other extreme is I can put it all the way at the other end. I can put x here, I can put x here, or anywhere in between. So basically, you're just optimizing that distance function on 0, 4. That answer your question? Forgot now who asked about 12, but that was how to do 12. All right, so let's go back to the questions that I just saw. So, no, sorry, there's a question about that now, and I don't mean to switch back and forth. Oh, you're talking about, sorry, you're talking about 12 from 12 from sapling, right? Okay. Recall that actually sapling is not the official homework for the class, but um, that's but anyway, maybe just ask me about that in office hours in that case. Sorry, there's some confusion about which problem that was. So, okay. So let me go back to the question about the rectangle and the farmer. So let's see. There we go. So how is it a closed domain in the farmer problem, but not this one? So basically, it comes down to the physics of the problem. Recall that in the farmer problem, basically what I was told is that the perimeter has to equal 120 because that's all the fence that I have. So I was able to set that up as, this is x, and this is 120 minus 2x. So there was kind of a physical limitation as to what I could set x to. I can't make x less than 0, but I also can't make it so great that the width of the fence is going to be less than 0. So that's what gave me that, x had to be less than or equal to 0 because I could just have no fence on the, coming out from the river. Sorry, not 0 is less than or equal to 0. And the most fence that I could run was 60 because then I had to run 60 there and back like that. In this problem here, although it is a rectangle, what I'm told is that the rectangle has 1600 area. So there is a set, let me just answer Eric's question. The question is because there's not a set quantity bounded to it. There is a set quantity in the picture frame problem. sorry, the other fence problem. There are different formulations of it, whether it's a picture frame or a fence. Um, there is a set quantity and its area. It's just that that doesn't limit how big one side is going to be. If I have only so much fence, then the perimeter does have a finite limit to it. If I say the area has to be 1600, I could make one side, like, I'm not drawing it this way, but I could make that, let's make it simpler. Let's say that this is 1,000. So I could make that 0.001, and then I could make this million, or I could make this 0.000001 and make this a billion. So the area doesn't limit the length. It doesn't limit the length of the perimeter the way a direct limitation on the perimeter does. So, okay. Okay, good. So let's do. Okay. So this is sort of, oh, so is there a problem where you'd have to go, let me just answer this question. Is there a problem where you'd have to go through two equations to get the answer, as in finding the derivative? I'm not sure what you mean by that, Julian. No, you shouldn't have to do that because you're always going to have one objective function. So if you have one objective function where the quantity to be optimized is written as a function of one variable, you're only going to have to find the derivative once. The only thing I can think of is, could you have one objective function that's, let's say, a case function or a piecewise function? So you'd have to actually find the derivative on either side of it. Yeah, that could happen. So you could, I'm just going to write here and then I'll erase it. I mean, it could be that your objective function looks like, x squared for x less than or equal to 1, and, it looks like, 2x minus 1 for x greater than 1. So you'd have to find the derivative in two different ways, but you'd still have one objective function. Okay. So anyway, this is sort of a more abstract type of problem. Again, these things are all sort of just, the strangeness of them is just translating the description into into the correct equation. So here the quantity to be optimized is the product of two numbers. So we want to be able to do is write that product as an objective function of the two numbers. So here we can say 2 is, let's let x and y be the numbers. So that gives us that, that the numbers are positive, so that's going to tell us something about the domain. So the sum of the first number squared and the second number is 48. So what that means is that x squared, or rather, let's actually write out the product. Product is equal to xy, but we know we're going to have to eliminate one of the variables. So we know that x squared plus y equals 48. And that gives us y equals 48 minus x squared. So you can see this is not a terribly difficult problem once you sort of get past the strangeness of what's being described. So that equals x times 48 minus x squared. So product as a function of x is going to be 48x minus x cubed. And the domain, all it says is that the two numbers have to be positive. So we know that x has to be greater than 0. And we know that y is such that since y equals 48 minus x squared, we know is that tells us that in order for y to be positive, x is going to have to be greater than the square root of 48. So that's really all we know, is that the domain is 0, 48. So we're not going to be able to use the endpoints because we have to have two positive numbers, and we're only looking for a critical number inside the interval. So here, of course, we can do is just find p prime of x equals 48 minus 3x squared. So p prime of x equals 0 implies that 3x squared equals 48, or x squared equals 16, or x equals plus or minus 4. So it's only plus 4 because we're looking for positive numbers. So we know that this is going to be, we know that the two numbers are going to be x equals 4 and y equals 48 minus 4 squared, which is, sorry, equals 16. There we go. Yeah. So 4 and 32 are the numbers. And we can verify that this is in fact the maximum, because if I take p prime prime of x, that gives me negative 6x. And if I plug in p prime prime of 4, since that was the critical number I found, I can easily see that that's going to be negative 6 times 4 equals negative 24. That's less than 0. So we have a concave down function sitting on top of the maximum, and we see that this is in fact a max and not a min. So that's going to be the answer. All right. Anyway, I'm out of time. Sorry, I'm a minute over. I'm out of time. So we'll say goodbye until Thursday, and that's when we will start chapter 5. Oh, don't forget, I have office hours coming up by WebEx starting at 12. Chapters the exam go up to. I'm going to make a formal announcement about this shortly. I think I announced it earlier, but the midterm exam is going to go up through 4.7, so it will include optimization problems. Chapter 5 will be reserved for the final exam. The final exam will be on the whole course, but it will also include chapter 5 problems.